Because a linked list is a very important data structure, rather than discuss a specific list such as list of integer or a list of strings, in this video I will discuss linked list as an abstract data type or ADT. Using templates, in this video I will give you a generic definition of linked list. Now let's review what are the basic operations on a linked list. Those are initialize the list, determine whether the list is empty or not, print the list, find the length of the list, destroy the list, retrieve the info contained in the first node, retrieve the info contained in the last node, search the list for a given item, insert an item in the list, delete an item from the list, and make a copy of the linked list. In general, there are two types of lists: sorted linked lists and unsorted lists. Sorted lists are those whose elements are arranged according to some criteria, and unsorted lists whose elements are in no particular order. What we will do for this implementation is that we're going to define three classes. First, we will define the class linked list type to implement the basic operations on a linked list as an abstract class. Using the principle of inheritance, we in fact will derive two classes, unordered linked list and ordered linked list, from the class linked list type. Objects of the class unordered linked list would arrange list elements in no particular order, that is, these lists may not be sorted. On the other hand, objects of the class ordered linked list would arrange elements according to some comparison criteria, usually less than or equal to. That is, these lists will be in ascending order. Moreover, after inserting an element into or removing an element from an ordered list, the resulting list will be ordered. If a linked list is unordered, we can insert a new item at either end of the list. Okay, recall that each node of a linked list must store the data as well as the address for the next node in the list, except the last node of the list. Therefore, the node has two member variables. To simplify operations such as insert and delete, we define a class to implement the node of a linked list as a struct. So as you remember in the past, here is what we have. So we have the struct and the node type is defined right over there. To maintain a linked list, we use two pointers, pointer first and pointer last, as you can see right over here, and an integer count. So basically the integer count is going to count and store the number of elements in the list, and the pointer first is going to be pointing to the first node of the list, while pointer last is going to be pointing to the last node of the list. One of the basic operations performed on a list is to process each node of the list. This requires the list to be traversed, starting at the first node. So moreover, a specific application requires each node to be processed in a very specific way. A common technique to accomplish this is to provide an iterator. So what is an iterator? An iterator is an object that produces each element of a container, such as a linked list, one element at a time. The two common operators that can work on an iterator are the increment operator and dereferencing operator. So as you know it from the past, plus plus for the increment and star or asterisk for the dereferencing. The increment operator advances the iterator to the next node in the list, and dereferencing operator actually returns the info of that current node. Note that an iterator is an object, so we need to define a class which will call linked list iterator to create iterators to object of class linked list type. The iterator class would have one member variable pointing to the current node, and as you can see, we have the class linked list iterator defined right over here, and the member variable is down here, which is actually the pointer to point to the current node in the linked list. Let's quickly review what do we have over here. So the public methods that we have a default constructor, constructor with a parameter. We have a function to overload the dereferencing operator star. Then we have the operator plus plus to overload the pre-increment operator. And remember, when we talk about overloading, we actually are talking about re-implementing those operators to work with the object of the type that we are dealing with. Then we have this operator over here, another overloading, so that we can overload the equality, another template to overload the inequality. So basically, inequality, equality, operator plus plus, dereferencing, and two constructors. Two constructors plus the overloading templates available to you. Also over here, you can see the definition of the functions of the class LinkedList Iterator, and every single prototype defined up there is actually fully defined underneath in the implementation. Now that we have defined the classes to implement a node of a linked list and an iterator to a linked list, next we describe the class linked list type to implement the basic properties of a linked list. So the abstract definition of this class basically defines the basic properties of a linked list as an abstract data type. As you can see over here, we have actually operators that overload the assignment operator. We have initializing list function, so this one basically initializes the list to an empty space. The isEmptyList function to determine whether the list is empty or not. Print is going to be the function to output the data contained in each node. Length is going to be the function to return the name of the number of nodes in the list. DestroyList is the function to delete all the nodes from the list. We have a function to return the first element of the list, which is going to be the front, and then back is the function to return the last element of the list. Down here again, we have a function to determine whether the search item is in the list or not. We have another function to insert new item at the beginning of the list, another function to insert the new item at the end of the list, and we have the delete node, which is the function to delete item from the list, and again another function to return an iterator at the beginning of the list, another function to return an iterator, one element past the last element of the linked list. So basically taking an iterator to the end or taking an iterator to the beginning of the list. We have a default constructor over here, a copy constructor, a destructor, and then we have the protected members that, as I explained before, integer count, first and last pointers. So the instance variables, first and last, as defined earlier of the class linked list type, are protected over here. As you can see, we want to make sure we only have access to those through a certain level of rules, but they're not private because, as noted previously, we will derive a class called unordered linked list and an ordered linked list from this class, and if we define these to be private, then they're not accessible by the classes that we're going to derive from this class. So we do the protection over here so that we can inherit those and use them in those classes. Also, because each of classes unordered linked list and ordered linked list in future will provide separate definition of the functions search, insert first, insert last, and delete node, and because these functions would access the instance variable to provide direct access to instance variables, the instance variables are declared as protected here. Again, I'm referring you to your knowledge about protected, private, and public members of a class. The definition of the class linked list type itself includes member function to overload the assignment operator as we just reviewed. For classes that include pointer data members, the assignment operator must be explicitly overloaded. Remember, we worked on this on previous videos. For the same reason, the definition of the class also includes a copy constructor and a destructor and a structure right here. Notice that the definition of the class LinkedList type contains the member functions CopyList, which is declared as private, the guy down here, right? This is due to the fact that this function is used only to implement the copy constructor and overload the assignment operator and nothing else. So far so good. Next step is going to be writing the definition of the non-abstract functions of the class LinkedList class. This implementation is based on the fact that the list is empty if first is actually a null pointer. Therefore, the definition of the function is empty list. To implement this operation would be this. So basically, we are going to return whatever is the result of first being equal to null pointer. True or false is going to be returned back, as this function is going to have the same thing. So the default constructor LinkedList type, as we discussed before, is quite straightforward. It is simply initialize the list to an empty state. And remember that when an object of the LinkedList type is declared and no value is passed, the default constructor is executed automatically. So this space is the full implementation of that. Now let's move on towards the DestroyList and look at that. Okay, so let me just scroll it up a little bit. There you go. So the function DestroyList deallocates the memory occupied by each node. We traverse the list starting from the first node and deallocate the memory by calling the operator delete. We need a temporary pointer to deallocate the memory. Once the entire list is destroyed, we must set the pointer first and last to null pointer and count to 0. If I scroll up a little bit, you're going to remember that the function that we have for the default constructor basically does the same. First is being set to null pointer, last is being set to null pointer, and count is being set to 0. So DestroyList does the same thing with a little bit differences we just explained. Now let's scroll down to get to the initializeList and see how this guy actually works. The function initializeList initializes the list to an empty state. Note that the default constructor or the copy constructor has already initialized the list when the list object was declared. This operation, in fact, reinitializes the list to an empty space, so it must delete the nodes, if any, from the list. This task can be accomplished by using a DestroyList operation, which also resets the pointers first and last to null pointer and set count to 0. Next in line is the printList function. So the member function prints the data contained in each node. To do so, we must traverse the list starting at the first node, because the pointer first always points to the first node in the list. We need another pointer to traverse the list. If we use first to traverse the list, as we discussed it before, the entire list will be lost. So that's why another pointer is being used here to traverse the list, and that is the current. As you can see, we define it. Now we use the current. Everything in first is going to be remain good, so we're not going to lose the address to the first member of LinkedList. Simply at this line, we set the current to be the first and then take care of it like a surrogate. So let's see, the next one that we're going to go to is to get the length of the list, which is the function over here. The length of the list, that is how many nodes are in the list, is stored in the variable count, and we discussed that before. Therefore, this function can simply just return count, and then we're going to have access to the length of the list. Next is how to retrieve the data of the first node. And that's what we implemented over here. The function front returns the info contained in the first node and is defined very straightforward over here. If there is something in first, then we simply return the information of the first as that. And you can guess the function back is going to do the same thing, but this time using the pointer back. Next thing we want to do is look at two functions, end and begin, or let's say begin and end in that order. The function begin returns an iterator to the first node in the linked list, and the function end returns an iterator to one past the last node in the linked list. Their definitions are very simple. You need to have an object of that class created. Remember, we talked about iterator being an object, right? And for the first one, we pass first to be at the beginning. For the last one, we pass null pointer to be at the end. And basically, we're going to return that object of the iterator in both cases back to the program. Of course, the logical next step is going to be talking about CopyList right over here. The function CopyList makes an identical copy of a linked list. Therefore, we traverse the list to be copied, starting at the first node, corresponding to each node in the original list, and we do first create a node and call it a new node, right? Then copy the info of the node in the original list into that new node, and basically then insert new node at the end of the list being created. So it's going to be member to member creation. We look at each node, we look at the data of that specific node in the current, and then copy it into node. So the key is current is going to traverse the current node, and new node is going to be the copy of current each time current traverses forward. This function has a couple of steps to make sure there is an item actually. So right here we check and make sure that we are not at the end of the list. And if you're not at the end of the list, you can just simply go through the lines of code. We read the info of that specific node and assign it to the new copied one. So current.info is whatever you see in the original link, and then you in original node, excuse me, and then you copy it to the info of the copy. Same story about the link of it, and we move on and easily make a copy of the entire list. And next thing that we want to talk about is the destructor right over here. The destructor deallocates the memory occupied by the nodes of a list when the class object goes out of scope. Because memory is allocated dynamically, resetting the pointers first and last does not deallocate the memory occupied by the node in the list. Remember, when we set those pointers, basically what happens is we remove that node from the linked list. However, the memory is still occupied. So what we have to do is we must traverse the list starting at the first node and delete each node in the list. The list can be destroyed by calling the function DestroyList as we discussed it over here. So now let's take a look at the copy constructor of our linked list. Because the class linked list type contains pointers and data members, the definition of this class contains the copy constructor. Remember that if a formal parameter is a value parameter, the copy constructor provides the formal parameter with its own copy of the data. The copy constructor also executes when an object is declared and initialized using another object. The copy constructor makes an identical copy of the linked list, and this can be done by calling the function CopyList over here, because the function CopyList checks whether the original is empty by checking the value first. We must first initialize the pointer first to null pointer on line 359, as you can see it. And then we can actually call the CopyList function. And the definition is going to be done within the CopyList. Next, let's talk about overloading the assignment operator, which is implemented over here. The definition of the function to overload the assignment operator for the class LinkedList type is actually very similar to definition of the copy constructor. We give its definition for the sake of the completeness over here. Rather than that, that's actually the same, that has the same principle and goes from there. So by this point, we defined our LinkedList class. Now is the time to move on and go and see how we can actually derive a class like unordered linked list and ordered linked list from that.